We were looking at phase noise of oscillators, and from the operation of the ring oscillator, it was clear that the noise gets accumulated in every cycle. You assume that initially you have a number of oscillators whose edges are synchronized, and then after that you let them run. If you have a free running oscillator, what happens is there will be some amount of jitter in each period. From period to period it is uncorrelated, but of course the next period starts after this period. So the absolute jitter, that is the comparison, how much the edge is displaced compared to an ideal noiseless oscillator, that will keep on increasing with time. The variance will linearly increase with time if you have thermal noise. Okay, so that showed us that the oscillator phase noise will do this. Fundamentally, at the very least, you will have this. Okay, so L of f will be some constant divided by f square. Okay. In addition to that, you will also have 1 over f cube component because of flicker noise, and then a constant component because of buffers and other constant noise that get added after the basic operation of the oscillator. The operation of the oscillator, it doesn't have an input, it's an autonomous system, right? That will definitely give you this 1 over f square type phase noise. In addition to that, you have all this, depending on if the transistors have flicker noise, you will have 1 by f cube component. And then of course you take the oscillator output, buffer it and so on, so you will have this constant component. Okay. Now we looked at this with the ring oscillator, and it turns out exactly the same happens with an LC oscillator also. So to do that, we used a very crude model of the LC oscillator. Now the model of the LC oscillator, which is actually fairly close to reality, is the following. This is the lossy tank. And then you have some GM in positive feedback, and GM has a characteristic like this, I versus V with a certain slope, and it saturates 2 plus minus I naught. Now this is of course real, and actually this models fairly well the class of LC oscillators which are made using tank circuits and differential pairs. Okay. Now of course in this case what happens is, for a part of the cycle you will be operating in this linear region, for another part of the cycle you will be operating in the saturation, and the analysis can be done, but it's a little more involved. So we use this, especially an extreme version of this, that is essentially a current switch, to calculate to estimate the amplitude. Okay. So we saw that across this you will have a waveform Vp cos omega naught t, where Vp is how much? 4 by pi I naught Rp. This is true for this current switch case, and then it's also true if it is somewhat linear. But as the GM values goes on reducing, it's no longer true. And if this slope becomes less than 1 by Rp, then it won't oscillate at all. Okay. Now to estimate noise, we will do something else. We will assume that the whole system is linear. This is the part that is not true at all. Okay. And we assume that this Rp has a current noise with spectral density 4 kT by Rp, and this minus Rp also has a current noise whose spectral density is Y times the spectral density is 4 kT by Rp. Okay. So now if you look at the transfer function from this noise sources, we can combine the whole thing into a single noise source, right? In to V0. This V0 by In this Rp cancels out with minus Rp, and you will have only 1 by the transfer function square will be that one, okay, or the transfer function magnitude will be so much. So this is basically let's see, I mean, let me write this down. So this will have, this is j omega c plus 1 by j omega L, and okay. So this one, what is this? This is basically 1 minus omega square by omega naught square, right? Where omega naught is the oscillation frequency, okay? And what is this? Now, essentially, we are looking at, so here again I will only look at the functional form. I am not interested in the exact expression that can be derived. I will just send you a handout. If you are interested, you will look at it. You can look at it. But right now we are only looking at the approximate, the functional form of this. So this obviously, this resonance has an infinitely large peak because there is no loss, right? The loss is compensated, and it will look like that. And we are also looking at a region which is fairly close to omega naught. Okay, this is what is known as close-in phase noise, right? Close-in phase noise means that you are looking at frequencies close to the oscillation frequency. So then, in that case, what can be done is the following. So in the numerator, you have this omega. You can just replace that by omega naught. Okay, because we are only looking at that around that one. So this whole thing, if you look at the functional form, it becomes okay. It is proportional to that, right? Is this fine? Now this is the magnitude. This is just, I am ignoring all the other factors. I am just showing you this part, and this itself can be written as 1 by, what is this? Omega plus omega naught times omega minus omega naught. Okay. So here again, assuming that we are only looking in the neighborhood of omega naught, so this part, the first one, can be approximated as what? 2 omega naught. It will be some constant stuff. It's not varying all that much. But this, of course, this will vary by a substantial amount. So this again, this part is not important. And this omega minus omega naught, this is what is delta omega, right? This is the offset frequency from the carrier. Okay. So this, what is the spectral density after all? It is the spectral density of noise times this transfer function magnitude square. So that's why you get proportional to 1 by delta omega square, where delta omega is the offset from the oscillation frequency. Is this okay? So now we know from our earlier analysis that if you translate the oscillator spectrum to DC, or rather if you look at the oscillator spectrum, what you see around the oscillation frequency, that is the phase noise spectrum, right? If you normalize the noise spectrum to the carrier power, that is the phase noise spectrum. Okay. So you can see that basically the phase noise spectrum is inversely proportional to the square of this offset. Okay. So again, so it is the same thing. So it is like saying L of f is proportional to 1 by f square. Here f, when you write L of f, it is the offset frequency, right? So in the LC oscillator also you get the same result. I mean, you can do a more rigorous derivation of this, but I just wanted to show you that it will be the same thing. Whatever kind of oscillator, because of thermal noise, you will have a phase noise that is inversely proportional to the offset frequency squared. It's very easy to see in the ring oscillator. It is very easy to see what's happening both in the time and frequency domain. The variance, essentially it's the number of clocks which are drifting off from each other. The variance goes on linearly increasing with time, and in the frequency domain you get 1 by f square, but the same is true for the LC oscillator also. Is this okay? Is this fine? So typically this is written as A by f square, A is some constant, okay? And of course this is plotted as on a log scale with dBc per hertz here, L of f versus f. You already looked at phase noise, so you are familiar with the units and so on, right? And the oscillator's phase noise will look like this. And it can also have f to the 0 means it's just constant, okay? Is this fine? So that's all that is there to it. At least for the fundamental this thing you can look at only this part, okay? Now it does turn out that for the same power consumption, the LC oscillator has a lot better phase noise, lower phase noise compared to ring oscillator. Okay, this is because the LC oscillator stores some energy in it, and ideally it will not have any energy loss. Okay, so this is measured by the quality factor of the LC oscillator. So the larger the quality factor of the LC oscillator, the smaller the energy loss in each cycle, is the larger the quality factor of the LC tank used to make the LC oscillator. Let me say that, because the oscillator itself that's not the issue. So the larger the quality factor of the LC tank used to make the LC oscillator, the lesser its noise will be. Okay. The intuitive way to understand it is that it has a natural tendency to oscillate by itself, right? The amount of energy that you need to feed in will be small. So consequently, the amount of noise that you feed in from outside as well as the noise generated internally will be smaller. Okay. Whereas the ring oscillator doesn't have any such resonance or storage. Okay. In every cycle, all the energy is lost and you will have a much higher phase noise. Okay. Now, of course, design also plays a role. That is, you can make a good oscillator or a bad oscillator. But from a fundamental sense, you can say that ring oscillator has a higher phase noise than LC oscillator, and you can also come up with some relationships. Okay. For both types, I mean, we have seen this with noise. Like, let's say you have a circuit and you have a certain amount of thermal noise, and you have to reduce that noise by a factor of 2. What will you do? I mean, without inventing a new circuit, which may or may not be possible, right? You have to do scaling. That is, essentially you take two identical copies of the circuit and connect them node by node. Then you will have twice the power and half the noise variance or noise cycle density. Okay, and exactly the same is true with LC oscillator. Okay, so the phase noise follows the circuit scaling and is inversely proportional to power dissipation. Okay. That is, you take a ring oscillator, let's say, and it has a certain power dissipation and a certain phase noise, and all you have to do is, let's say, you take two of these and connect them node to node, then this will have 2 times the power dissipation and half the phase noise. Okay. First half the phase noise spectral density, the same goes for integrated jitter and all that stuff. Is this okay? Then the same, exactly the same holds for LC oscillators also. Okay. Now one more thing is, how does it depend on the oscillation frequency itself, the phase noise, right? That is, let's say I design a 1 gigahertz oscillator and you design a 2 gigahertz oscillator, right? And we have used the same sort of techniques, maybe the same inverters and so on. Okay. So how will the phase noises compare, do you think? I mean, there is no, you have to just guess, like, so now, of course, it is not clear like how much power is consumed in each one, right? But assuming the same power is consumed in each one, it turns out that again, all these things can be rigorously derived. I am not doing that. I am just giving you the arguments. And I am assuming the same type of oscillator. I am not assuming that I design a bad oscillator and you design a particularly clever oscillator or vice versa. Okay. It's the same oscillator, but I just somehow change the components to change around the frequency. Okay. L of f, it turns out it is proportional to f naught square. Okay. Where f naught is the oscillation frequency. Okay. Now again, I won't derive this, but one plausibility argument I will give you, that I have a 1 gigahertz oscillator and it consumes a certain power PD. Okay. So this gives a 1 gigahertz output with a certain phase noise. Okay. Now let's say I have a 2 gigahertz oscillator and at 2 gigahertz it has a certain phase noise and I can divide that by 2. So now I get a 1 gigahertz output. Okay. Let's assume that the oscillator consumes PD and the divide by 2 consumes 0. This is not realistic, but let's just assume that. Okay. So then fundamentally it turns out that these two will have the same phase noise. Okay. That is, I can't just get into, I can't do some magic by, instead of making a 1 gigahertz oscillator, I make 2 gigahertz and divide it by 2. I can't get something better. Okay. It turns out this will have the same phase noise. Okay. So here the phase noise will be L of f. So what will be the phase noise here? What is the relationship between the input and output phase noise of in a frequency divider? It is? What's that? N square. Yeah. So we saw that for narrow band, that is low frequency phase noise, it will be N square, and if it is white, it will be N, factor of N. But here we are looking at 1 over f square shape. Basically it is emphasized at low frequencies, right? It is like a low pass type noise. So this will be 4 times L of f. Okay. So at a fundamental level, if you use the same power dissipation, you will get your phase noise will be proportional to f naught square. Okay. Is this fine? So now it turns out that people have come up with some figure of merit to compare different oscillators which may be designed for different frequencies, are designed using different power dissipation and so on, to get rid of all of these factors and then find out something, make a meaningful comparison. Okay. So again, there is physical significance to all this. I am not giving you that, I am just giving you the results. We said that the phase noise, first of all, is inversely proportional to the offset frequency squared. Okay. And it's also proportional to the oscillation frequency squared. Okay. And it's inversely proportional to the power you dissipate. Okay. And times some constant. Okay. So now this constant alone is a measure of the quality of your design. The other things will always come, right? For the same type of design, the phase noise is always inversely proportional to the offset frequency square, or it will be proportional to oscillation frequency square, or it is inversely proportional to power dissipation. Because I can take your oscillator, take 2 of them, connect the node to node in parallel, and then claim that I have an oscillator with lower phase noise. That's fine, but what did I do anything that is intelligent? Nothing, right? What is the price I am paying? I am burning twice the power. Okay. So to measure the quality of oscillator designs, essentially you have to look at this factor alpha. Okay. So what is alpha? Alpha would be L of f, f square by f naught square times the power dissipation, and the lower the better, right? If alpha is smaller, that is better, isn't it? That's a better design. So you compare the values of alpha, or many times you compare 1 by alpha. It's the same thing. It is basically 1 by L of f, f naught square by f square, 1 by PD. Okay. So if you define it like this, the higher the better. The reason I am telling you all of this is that from this figure of merit you can estimate the phase noise given the power dissipation without going into the details of the oscillator itself. Okay. So now conventionally it turns out this lower one, this is what has been used. This and that are just reciprocals, and in fact it is usually expressed in dB, so this will just be the negative of that. Okay. So now it turns out that this is what is used with a slight twist, the oscillator phase noise figure of merit. It's given by, first of all, a logarithmic unit is used. Okay. And then you have exactly all of this. Except conventionally, because this was come up with IC designers who are designing oscillators with power in the range of milliwatts, this power dissipation is in milliwatts. Okay. This is the figure of merit. Okay. Pardon? Correct. So for an LC oscillator, alpha depends on Q and so on. So if you manage to get a better Q, you will have a better number. That's actually a very important thing. It does depend on Q. Okay. And very roughly, this number for CMOS oscillators, this again depends on the frequency range and so on. There are a lot of engineering details that go into an oscillator. It's not as though, just because I design 1 GHz oscillator with a certain figure of merit, I may not be able to design a 1 Hz oscillator because of constraints on components, right? Because the R and C's become very large. On the other hand, I may not be able to design 100 GHz oscillator at all, right, in a given technology because the oscillator just won't work. But roughly speaking, this figure of merit is about 165 dB for CMOS ring oscillators and 185 dB, 185 to 180 dB for LC oscillators. It can be higher, like he very rightly pointed out, it is actually proportional to Q square. So if you somehow manage to get a better quality tank circuit, better inductor and capacitor, it is you can get a higher figure of merit. But very roughly you can use these numbers. Okay. So 185 to, let's say 185 to 190 dB for LC oscillators. Okay. So using this, please calculate the following. This is just a small exercise because a lot of this is opaque now, right? Unlike the other stuff which I dealt with in detail, here I don't want to spend too much time on oscillator phase noise, but I'm just giving you the results. The main result is you have 1 over f square phase noise. You also have 1 over f cube because of flicker noise. That's not difficult to understand because white noise gives you 1 over f square, 1 over f noise gives you 1 over f cube. And because of this added white noise, that is after the oscillator passes through buffers, right? So if you have white noise there, you will have a white noise part here also. Okay. And because this phase noise is a little bit abstract and we don't want to, and the analysis from the circuit level is difficult. Okay. Whereas for a amplifier or a filter, they will have a DC operating point. You can find the noise spectral density of each component, transfer functions to the output and calculate the noise. In an oscillator, it's more difficult because the oscillator undergoes large signal excursions. So you can't define a DC operating point. Okay. You have to take a periodic operating point because the transistor can go all over from off to saturation region to triode region and so on. Okay. So the operating point varies substantially and there is a class of analysis for this which is basically related to periodically time varying systems. Okay, where the small signal parameters, normally what you do, you take the DC operating point and you take the small signal parameters at that operating point. Here also you do the same thing except the operating point is varying periodically. So GM and GDS, everything will be varying periodically. Okay. So analysis with all of that is a little more involved. So we won't get into that in this course. Those of you who are taking advanced electronic circuits will probably see some of that. Okay. And you do have the simulators which do take care of that. The periodic steady state analysis in circuit simulators do take care of this one. Okay. So anyway, let's do a quick exercise. Calculate the phase noise of ring and LC VCOs. For ring VCOs, assume that FOM is 165 dB and for LC VCOs, assume that it's 185 dB. Okay. I'll assume a 10 GHz oscillator and a 10 milliwatt power dissipation. Okay. So with this assumption, calculate the phase noise at 1 megahertz offset. Okay, please do this. It's a simple calculation. It's just means substituting It just involves substituting the numbers correctly into that expression. By the way, this FOM itself, the figure of merit is 10 log 10 1 by L of f times f naught by f square 1 over PD in milliwatts. Okay, so that means that you should put 10 milliwatt 10 here, not 10 to the minus 2. Okay. This itself can be written as basically minus 10 log 10 L of f, which is, this is just the negative of the phase noise in dBc per hertz, right? Plus 20 log f naught by f, okay, and minus 10 log of PD milliwatts. Okay. So I have 165 dB to be this negative of, I'll just write it as L dB of f. This is the phase noise in dBc per hertz. In fact, it's usually described in dBc per hertz. And how much is this? F naught by f is, this is f naught is 10 gigahertz and f is 1 megahertz. So this is 10 to the 4. So the whole thing is 80 dB, right? Minus 10 log this is minus 10 dB because PD is 10. Okay. So L dB is simply minus 165 plus 70 equals minus 95 dBc per hertz. Okay. And for the other case, it's straightforward, right? What will it be? It's 20 dB better, right? That's all. So if you have 185 dB, it will be minus 115 dBc per hertz. Okay? Is this fine? So this, the reason I am giving this is that without going into the details of the oscillator, I'll just give, let's say, the FOM and you can calculate the phase noise. Okay? Or FOM and the power dissipation. So this is also a good estimate, I mean, to know what a ring oscillator can do and what an LC oscillator can do. Okay? So let's say you did want this, you wanted this minus 115 dBc per hertz. Okay? So you know that an LC oscillator can give you this with a 10 milliwatt of power. Now let's say you don't want to use an LC oscillator, sometimes there are good reasons not to, that is it takes too much area and so on, the inductors take a lot of area, that's the reason to prefer ring oscillator. But can you use a ring oscillator here? If you wanted to design a ring oscillator and get minus 115 dBc per hertz, how much power would you need? I mean the same design, same everything, so how much power would you need? Yeah? 100? 100 times, so basically 1 watt. Okay, now of course that's a tremendous amount of power, so that may not be possible at all. So this is also the kind of thing that lets you decide between a ring oscillator and an LC oscillator. Okay? Is this okay? So the main qualitative conclusions are what I showed here. Phase noise is proportional to 1 by f square. It also has 1 by f cube and constant this thing. And a ring oscillator has a higher phase noise than LC oscillator. And how much higher? About 100 times higher. Okay, roughly speaking. It could be more. I mean, by the ring oscillator, you can't do much to change its phase noise. Okay. All you can do is, typically you calculate some noise based on fundamental considerations. And in practice, it will be worse than that. Whatever those engineering parts are which are worse, you can try to minimize, but obviously you can't go below the fundamental limits. Whereas the ring oscillator, LC oscillator, if you somehow manage to get a higher quality factor, you will do better. Okay? And these are the sort of quantitative things that you assume, if you have no other knowledge, you assume these figures are merit for ring and LC oscillators. LC oscillators can be better than this, but if you put in all the details, it will come down to this one. And then calculate the phase noise, okay, based on the power dissipation, or calculate power dissipation based on the phase noise required, and so on. Is this okay? Then we came to all of this while calculating jitter generation. VCO has its own phase noise. The jitter generated due to the VCO, how do we calculate this? Essentially, we have to find out the phase noise due to the VCO will be, the phase noise of the VCO will be this one. Okay, and this has to be multiplied by evaluated at S equals J 2 pi f, okay, and the jitter should be 2 times the integral of this from 0 to infinity, okay. This is fine. Now what did this come out to? This was S square by omega u omega z, I mean all the terms as defined earlier, 1 plus S by, what was it, omega z, right, plus S square by omega u omega z. Now the important thing is, in the other cases, when you had a band pass or a low pass, the integral of the transfer function itself was convergent. Now you can't integrate this from 0 to infinity, right, you will get infinity. But what happens, this you have to take the magnitude squared of this and substitute S equals J 2 pi f, okay. And what is this now? This is some constant by f square, okay. And I will write it like this, I will make it 4 pi square a by 4 pi square f square, okay. So then what happens? This 4 pi square f square can be cancelled with one of the s's there, right, because you have a square over there also. This is okay. So now, and I will take the omega e square outside, I have that, and this integral you know, s by omega z by 1 plus s by omega z, this whole thing, this is the band pass stuff, right. What is it? What is the integral of this? Omega z by 4? Omega u by 4, I think. This is omega u by 4, okay. So the integral of this will be omega u by 4, okay. So you can find the jitter due to the VCO. What is that? It's, you have a 2 outside, so it will be 8 pi square a, this 4 is here, so 2 pi square a divided by omega u, okay. So the answer comes out quite simply as well, if you know, this is assuming only 1 over f square type phase noise, right, only 1 by f square type phase noise, but the jitter generated due to the VCO is this. Does the answer make sense? 2 pi square a by omega u, it's inversely proportional to omega u, does it make sense? Yeah? Correct. Basically, we essentially clean up the VCO as far as the bandwidth, right? The higher the bandwidth, below the bandwidth, we are suppressing the noise of the VCO, right? That's the first approximation. So below the bandwidth, whatever noise VCO adds, the loop will track it and cancel it out. But above the bandwidth, the VCO's noise will come out right away. Okay. So now, because then obviously, then as you increase the bandwidth of the loop, the contribution of the VCO decreases. Okay. Is this fine? So the answer also makes sense. So very quickly, let's do this calculation. We assume a VCO like this, okay, and let me assume a bandwidth of 10 megahertz, which is a rather high bandwidth, okay. So calculate the mean square jitter in phase as well as time. Okay, for the same oscillator, what were we considering? We were considering a 10 gigahertz oscillator, right? And you have to calculate the value of A that you know. Okay, so please do the calculation. For the same oscillator as earlier, that is an oscillator which used like 10 milliwatts of power and had a figure of merit of 165 dB or 185 dB for ring and LC oscillators. And with that oscillator, you place that oscillator in a CDR of 10 megahertz bandwidth. What will be the jitter contribution due to the VCO alone? That's what we are calculating. Okay. Again, it's just substituting formulas, but please do that and we'll continue the discussion. Okay. You need the value of A, but you can calculate it from this, the phase noise stopper. So please do that and we'll continue the discussion. Is tomorrow a holiday or something? Okay. Yeah, it's a holiday.